Just for 40 minutes.
Yeah. Okay. All right. I guess everybody understands now. Okay. So, Mr. Yu, could you give a presentation and
Yes.
also
Sure.
questions?
Okay. First, I want to say thank you to all of you to coming to my thesis defense. My name is Wu Yu, a PhD candidate from the computer science, and my supervisor are Dr. Wu and Francis Law. Today, I want to introduce some of our research work on how to deliver multimedia content through the geo-distributed cloud. Studies show that internet video data has occupied over 25% of all inter-AS traffic, and this phenomenon brings challenges to the application providers and end users and the data center owners. The talk can be outlined as follows. I want to introduce the motivation and background from 3 different perspectives, and then I will introduce 3 exact problems we have solved. It's how to scale the social media application to a public cloud, and then later a prototype named Cloud Move. It's a cloud-based mobile social TV, and then I'll introduce some work on how to enable bulk inter-data center transmissions. Last, the conclusion. First, the motivation. From the perspective of application provider, if we look at the top side here, we can see that there's an increasing number of social applications like Twitter. And there's another type of application, we call it user-generated content like YouTube, where users can upload their own videos to make it public to all the other users, either friends or strangers. And there's a trend of these 2 kind of application. And this kind of application usually, for example, a Twitter user may tweet a hyperlink of his recently uploaded video to his friends, and his friends can watch the video. And later, maybe his friend can retweet the message to their friends. And this is just a propagation process of the video. This kind of application, we name it a social media app, have usually highly dynamic contents. And some studies show that YouTube video, if the latency of YouTube video is higher than 150 milliseconds, the YouTube users will not be happy. And another challenge is users all over the globe. Traditional approach is that application providers are tending to use dedicated servers, but this is not good because the user requests are dynamic. If we over-provision the resources for the peak request, it will be a waste of money. But on the other hand, if you under-provision the resources, the applicant provider may lose the market, so neither are good. So the intuitive thought is that can cloud computing help here? Many people or institutions try to define what the cloud computing is, but the general agreement is that cloud computing can provide flexible resources to the users in a pay-as-you-go manner. There have been a lot of companies have entered into this market, which may be worth hundreds of billions of dollars, and they have built their own data centers all around the world. And this kind of cloud system usually can provide infinite resources, and also they can push the content to the edge of the network to decrease the latency experienced by the users. But there are some practical issues to be addressed. How should the content be stored or migrated? And how to distribute the viewing request to bump the latency requirement and still minimize the optional costs. It seems that all an algorithm is necessary because this kind of system is highly dynamic. Users come and go, and the contents are also dynamic. But still, we want to approach the offline optimality. Second, from the perspective of end users, we think that it's maybe kind of interesting to consider the mobile users. And the smartphone market grows a lot since the iPhone was released in 2007. And until now, there are over 1.5 million Android devices are activated every single day, and there are over 1 million iOS applications on the Apple App Store. Nowadays, the smartphone usually have powerful CPU and gigabyte RAM, and the smartphone can be have a 3G or LTE network. And these powerful devices usually can bring a rich multimedia experiences to the mobile users. But still, we can see that the performance of the mobile phones are still lag behind the PC, and users carrying a phone maybe move around when the signal is not good, the connection is not stable. And perhaps one of the most concerned problems on mobile phones is the battery. There seems a conflict. The more powerful of the mobile devices, it seems that it's tending to consume more energy. And another hand is the size of the mobile devices are so limited. They cannot put a large battery into the mobile phone. So it seems that the battery will always be the headache. We also think that the cloud computing can help here. It's an intuitive thought that the ubiquitous accessible computing or network resources in the cloud meet well to the resource efficiency on the device. But some practical issues are here. How to effectively exploit cloud resources, how to reduce the battery consumption, and the user want to enable a social interaction between their friends using their mobile phones. And another problem is that we all know that in the market out there are different phone platforms like Android phone or iPhone. How to make our solution easily portable to all those platforms is a challenge. Third, from the perspective of data center owners. Now, data center owners are building their data centers all around the world. This figure shows the Google data center in the North America. We can see there is a basic demand is that they want to transfer bulk volumes of data from one data center to another. But this is not easy because most of the current data centers are built on top of legacy system like TCP/IP network, which was not designed for, which was only designed for best effort transmission. So it's kind of difficult to deploy a new scheduling algorithm or a brand new architecture on those existing systems. Here I want to briefly introduce ISDN paradigm. Traditionally, there are two function modules, the control plane and the data plane on a switch. The control plane will control the routing's intelligence, and the data plane will be responsible for transmitting data at a line rate. Traditionally, switches tend to combine these two modules into one single box, but SDN paradigm advocates to make a clear decoupling between these two modules to abstract out a control plane. By this paradigm, we can deploy a new scheduling algorithm very easily on those existing systems. But there are also some practical issues. The inter-data center links are limited, but in reality, the inter-data center traffic are huge. They will contend for the limited bandwidth. So how to solve this problem?
Dr. Wu, Professor Lau just called. He will be late around 15 to 20 minutes. You can start it first.
Okay, thank you.
And those transmission requests usually have different deadline requirements. So this is maybe some important information we can make use of. And the third is we want to enable reliable transmission. By reliable transmission, we mean that if some transmission request is issued, if the data center owner accepts the job, we cannot let it fail. That is what we call reliable. And the last one is also important, how to practically implement such a system. Now, I will introduce some exact problem we have solved. First is, from the perspective of application provider, how can we scale the social media application to a public cloud? Now, there are some related work. there are a series of working on the standards to enable such an ecosystem to federate the cloud system from different vendors. But our work, I think, complements theirs well. What we are doing is trying to investigate how can we efficiently utilize the geo-distributed clouds to enable multimedia applications. And there another group of work is that they are trying to migrate application to public cloud platforms. There is a difference of our work. We are trying to solve this problem from a different angle. We try to migrate a large-scale social internet application. This is a little different. The third one is content deployment on CDN or cache network. I think those work are handling a relatively static situation where the number of contents and the number of users are relatively fixed. But we are trying to solve a problem. There are dynamic contents and dynamic users. And we also, another difference is that the charging model of traditional CDN network and the cloud system are different. So it's necessary for us to design a very highly efficient online algorithm. We assume that there are geo-distributed clouds spanning different regions. At each region, there are computing servers and storage servers. For simplification, for our analysis, we assume that all servers at the same region have the same configuration and the same cost. And following the public commercial cloud system, we also model our cost according to theirs. The storage cost, computing cost, this is related to the virtual machine instance. And the user also should pay for the traffic cost they use. And there is a migration cost because application provider may want to migrate their contents from one data center to another. User belong to the region that they are closest to. This is another simplification in our model. Our objective is we are trying to optimally replicate videos onto cloud sites and how to dispatch those video requests to the sites to minimize the operational cost and also make the latency bounded. We model our cost because our system runs in a time-slotting manner, just similar to the public cloud system. There are storage costs for each time slot, and we combine the computing cost, the traffic cost, after some mathematics, combine them into a single one. And there's a migration cost for each data center for those newly migrated content. We can solve the problem into optimization problem. We try to minimize the overall operational cost for each time slot to make the latency bound that the constituency. And before serving any multimedia to the users, the content should be replicated to that cloud site beforehand. If you look back at the optimization problem, it seems that it's a mixed integer problem. It's going to be hard. But we can prove that it has efficient solutions through dual decomposition. A summary of the solution is that there are two important decision variables. It's the y and alpha. Y is the replication decision, whether to store a content at a cloud site at a certain time slot. We can prove that given the replication decision, the request dispatching decision can be efficiently derived because after this is given, it is a linear problem. If we can solve this problem, we can still see that this is a one-shot optimal solution. We still want to adjust this one-shot solution towards an offline optimal one. For example, for any time t, the one-shot content placement for any video C at region F equals either 1 or 0. If it equals 1, it means we should store a copy of that content at the cloud site F. If y equals to 1, we can prove that it's also offline optimal to keep the value. Otherwise, if y equals 0, we will show it's non-trivial to decide the offline optimal solution. Now here's an example. For this time slot, if the one-shot optimal solution y equals to 0, how can we decide? Because if we follow the one-shot optimal solution, at the next time slot, we have to store that content again according to our scheduling algorithm, the one-shot optimal solution. So maybe we should keep that content. Otherwise, we may waste an extra migration cost. So we propose our look-ahead algorithm. The idea of the algorithm is that from this time slot, we look forward 30 time window and consider two series. Series 0, we assume that we will assign y equals to 0 at this time slot and compute the series according to our optimization solution problems. And another series is that we assign y equals to 1 and compare these two series in the window. We can prove that if series 0 is not larger than series 1, we can keep the one-shot optimal solution. Otherwise, we should adjust the one-shot optimal solution from 0 to 1 to get the offline optimal one. So that is the basic idea of the algorithms. Next, I want to introduce a prototype. It's named CloudMove. It's a cloud-based mobile social TV. There are some related work here. A number of mobile TV systems have sprung up, but we should say that those work are mainly targeting at the convergence work between the traditional television network and the mobile network. And the second is that they didn't consider the unique challenges on mobile devices. And another series of work is on the power consumption. I think most of the work are targeting at optimally adjust the CPU level. But some studies show that on the mobile devices, the most energy consuming power modules are the display and the wireless transmission module. So we try to handle the power consumption problem from a different angle. We try to optimally transmit the video streams on mobile devices to save the energy. The third is there are a series of very inspiring work on cloud mobile computing. I think most of their work are still trying to optimize how to offload the computation-intensive job to a cloud system. But our work consider both the computation-intensive job and also the try to optimize the network transmission. I will introduce details. Our objective here, we try to design a full-featured mobile social TV and try to stream alive or on-demand video from any video resources. This can be on-demand, and also if the broadcast address of a live event is public, we can still support that show. Second, we want to provide a co-viewing experiences to the mobile user. By co-viewing experiences is that even some friends are located at different places. We want them to join into the same section, and even they can forward or backward the show for a VOD video. We can guarantee they'll still watch the same part of the show, and they can, during watching the show, they can maybe exchange or do social interactions with each other by text messages. Here is the snapshot of our system. There are a login gateway. After user log in, the user can subscribe a video show, and he can even see a group his friends. Actually, these people are our group member, and he can see whether his friends is online or not. If it's online, he can select to invite them to join in the same session. And during when watching the show, they can chat with each other. It's kind of interesting. But one thing I want to mention here is that it seems that we developed a native application, but we didn't, because all those GUI are just browsers. So we cannot solve portability issues. As long as user mobile phone have an HTML5 enabled browser like Safari or Chrome, they can use our system. This is an overview of the architecture of the cloud move. So for each mobile user, it will be assigned exclusively a surrogate from an IaaS cloud. For example, Amazon EC2. And this surrogate will work as a proxy between the external video source and the mobile user. User do not directly watch the internet video, but they will just watch the process the video by the surrogate. And the function of the surrogate including the surrogate will transcode the internet video or TV show to the appropriate bitrate and the codec the mobile phone can support. It's highly dynamic. And there's another module which is very interesting, the synchro named. Because in the same session, when user watches the same video, our synchro will work behind the scene to synchronize the playback time, the time point when where user watches a portion of the video. It's enabled by a very important property on HTML5. It is the current time property. So we periodically synchronize the playback time. So we can guarantee user will watch the same part of the video show. In this system, we also use a social PaaS cloud. For example, Google App Engine. Why do we do that? There are some reasons. One, because we trust Google. Google can provide a scalable platform. And the second reason is we don't want to reinvent the wheel because Google can support very scalable social message dissemination using their big table like a data store. We can bring it, just use it. And second is, the third reason is that we want to do a proof of concept to see whether those public cloud, the performance is good enough. The social cloud will be communicate directly with the surrogate. Mobile users cannot see this public cloud. It is used to disseminate the social messages, like whether the users are online or not, whether if mobile user send a text message, he will just send a message to the surrogate. Surrogate will forward that message to the social cloud, and the message will automatically disseminate to all the users in the same session. Another interesting module is Reshaper. I'll introduce it in details. Now, we all know that the battery issue is a very important one. According to the 3G network spec, for a mobile user, we name it user element. When the mobile device is transmitting the data, the mobile devices will be regulated by a video resource control state machine. The mobile devices will be stay in different energy level. If the mobile user is transmitting a lot of data, it will be in active mode. After it transmitting the data, it will stay in the energy level for a short time. That short time we name it preheat inactivity timer. It is dependent on different carriers and mobile devices, so we should measure it using our real-world experiments. So the high-level idea is that if we can, from time to time, let the mobile devices to drop down to a lower energy level, we can have a good chance to save the energy. But this time is dependent how can we transmit the data. So our idea is try to chop the video stream into chunks and transmit the chunks to the video user in a burst mode. How to decide the length of the burst size? We can try to solve very easy mathematical equations. This represents the cost saving if we use the burst mode. Otherwise, this is continuous downloading. A general idea is that we cannot let the chunk size is too small. Otherwise, because there is a delay before the energy level dropped, if the chunk size is too small, the mobile user just cannot wait for its time to sleep. So this formula can derive a lower bound of the burst size we can choose. So the reshaper just means that we chop the transcoded video stream into chunks and just do traffic reshaping functions. We implement our prototype into the IaaS cloud. The IaaS cloud is we choose Amazon EC2, and the social cloud we choose App Engine. There's a workflow for internet video. It will be transcoded, and then it will be encapsulated into a transport stream. That is for convenience to the later job. That's the segmentation. We try to chop the video stream into chunks, and after it's done, actually after the first segment is done, the user can directly download the video from the surrogate. We should say that to increase, guarantee the performance, all transcoding, encapsulation, and segmentation modules are implemented using standard C. The other logic, we deploy them into a Tomcat servlet container to make it easily portable to other public cloud. For the social cloud, I want to mention that what we mainly use is the big table of the Google, the dashboard, because it's very scalable and the latency is very short. We will show it in the experiment. And we choose not to use the lower level API support provided by Google because we don't want to lock our system into a specific cloud system. So we choose the JPA 1.0 API interface. In other words, we can, as long as there is another PaaS cloud, it has a big table like HDFS, and also support the GPA interface. We can port our system to the other public cloud. So here are some experiment results. We are using a NBA video clip because when we do the experiment, Jeremy Lin is performing fantastic for the NBA game. And I want to mention that this is a flash. iPhone cannot play back a flash, but for our system, we can dynamically transcode the format to a compatible format, so we can watch the video. We use 3 types of virtual machine instance. We can see when the burst transmission size grow, the latency will grow because there are more jobs to do. We have to transcode more video. But when the size is bigger than 60, it will grow very quickly. I think it's because we are using a very cheap virtual machine instance, and the CPU and the memory are very crucial here. So when we implement our prototype, we choose a burst size which equals to 60 seconds. Now here's in this experiment, we try to simulate a 3G network. Because 3G network is random, it cannot reproduce our experiment results. So as simulate a 3G network environment using Wi-Fi, we can dynamically change the available bandwidth. And we can see the bit rate of the video stream can also change dynamically. This can provide a smooth playback experiences. Also, we all know that because we select Google App Engine, the performance of their cloud system is very crucial for our system. So we test the latency when the user sends text messages. We measure how soon of the other users will receive the message. We can see that the latency most of the time is very short. Now here's a very interesting consumption because we want to testify whether our burst mode transmission can save the energy. We compare a burst size which equals to 60 seconds and another is size equal to 10 seconds, we can see for 10 seconds, the energy level of the mobile devices never drop. For the 60 seconds, we can see this is quite mapped to the theoretical analysis of our analysis in the previous slides. The energy can drop, can sleep for a while, and then increase again. We can show that our system can achieve a 29.1% increase of battery lifetime. Of course, I want to mention when we do the experiment, we turn off, we make the brightness of the display too dark because the display will also consume a lot of energy. Next, I introduce a final work. It's the bulk inter-data center transmission. We assume that the cloud spanning multiple data centers located in different geographical locations, and the connections among the data centers are dedicated full duplex links. Data transfer requests may arise from any data center to move the volumes of data to another, and each request has a deadline requirement. Our promise is that once, this should be accepted. Once accepted, the transfer is not allowed to fail. There are some also related work. For example, some of work like this one, they just assume the transmission are a flow level. The transmission has an infinite date to transmit. This is not practical because they assume a flow level model. In our work, we assume a chunk level model. And another work, their work are trying to assume that they know the request pattern, so they can accordingly, proactively scheduling. But in our work, we have no such assumption. Our system can work in a generic environment. And another work, they are trying to increase the internet data center network utilization. We should say that the purpose of our work is different from theirs, but their work are still very inspiring to us for our future work. Now, this is a simple illustration how the system works. For each transmission request, there is a source node, a destination node. TJ represents the earliest time slot the transmission can happen, and capital TJ represents the deadline of the transmission. And each job will be associated with a utility. And the circle represents the data center. Between each data center, there is a dedicated link. There is a bandwidth. We define the bandwidth as a multiple of a unit bandwidth. And before transmission, the data will be chunked into equal size chunk. And we define the chunk size is that it will take one time slot to transmit a chunk from one data center to the neighbor data center. So that's basically the model. When we can design the scheduling, each chunk can transmit according to their own scheduling path. And also, it is a multi-hop transmission. The high-level idea is that for those jobs which has very loose deadline requirements, they can stop at intermediate data center for a while and to make way for the emergent, urgent transmission job. And after the bandwidth, after those urgent job is finished, those job with loose deadline requirements can reattend the link and continue with their transmission. And so far, this looks like a bandwidth reserving, but we do not like that. Think about this situation. If the blue job, the routing path has been calculated for the blue job, and it can follow the path. But at some time slot, when it reaches the intermediate data center, if there's a new transfer request issued, like this one, if it has a very tight deadline requirement, maybe it wants to use this link immediately. But according to our pre-calculated decision, it should be rejected but our system can support such dynamic situation. The blue one will calculate a new path, and both this job can be completed. We also use optimization, try to maximize the system utility. But here we consider both the newly arriving job and those previous accepted job, but they have not been completed because this is our promise. And we try to make the constraint here. For those previous accepted job, we should make the job still accepted. And another constraint describes that for any intermediate data center, if they want to help forward the chunk at a time slot, it should receive that chunk at a previous time slot. And to make the deadline requirements satisfied, each accepted chunk should be transmitted no later than one time slot before the deadline. Because in our model, we assume that each chunk will take one time slot to transmit. Now here are some prototype implementations. We name it as DTM system, delay tolerable migration. And there's a central controller. We are using the SDN paradigm. The central controller is implemented on top of the beacon framework, which is also open source. And for each data center, there is a call switch. And the data center will connect it through the dedicated link through the call switch. Because when we calculated scheduling decision, the controller will be translate the language to open flow API. It can be understandable by the call switch and change the flow table, the decisions are made. But we should say that the call switch has no intelligence. We should deploy a gateway server into the data center to help the controller to achieve all the job. And the message interaction between the gateway and the controller, we are using a JSON RPC. It's very lightweight text-based interaction. Now, here are some simple modules. I don't want to introduce the workflow. For any user belonging to a data center, if want to deliver some transmission requests, the job aggregator will accumulate all those requests. And then the gateway server will forward the job to the request handler in the controller. And the request handler will return a job ID, which is convenient to reference that job. And there are two independent threads still working all the same in the background. For the request handler, periodically the scheduler will fetch the request in a burst mode from the request handler queue. And after receive it, it calculates the schedule. And if the job is accepted, it will tell the user and the destination data center to let them know the job is successful. Otherwise, it will explicitly tell the user the job is rejected. And there is another thread, if periodically the scheduler, the command dispatcher, the scheduler will update the command queue. Each command object in the command queue will be a decision telling which chunk when should the chunk should be transmitted. And the command dispatcher will scan through the command queue to choose the decision, the transmission which should be happen at the next time slot. And the controller will tell the gateway server to put the chunk onto the call switch at the next time slot. And the call switch will automatically transmit the chunk to the destination according to the updated flow table. So this is just a basic introduction of our module. Here's the conclusion. In this talk, from the perspective of application providers, we try to enable a social multimedia application in the geo-distributed cloud. And also, from the perspective of end user, we introduce our work. We want to think how the cloud computing can get the strength, get the power from the cloud computing services. And last, we present a deadline of about data transfer across geo-distributed data centers. And some future work is that in the first work, we only consider the cost minimization, but from the perspective of application provider, they may be more interested, also interested in how to maximize their revenues. So these factors are all what we have to consider in our future work. And for the second work, the cloud move, we are using a Google App Engine, but we should say that Google App Engine and other PaaS cloud, if they can support the big table data store like Hadoop, HDFS, they can support memcache. So if possible, we want to incorporate the memcache function into the cloud mode to increase further decrease the latency. But still, we will stick with our principle. We are using open standard. We will select the GSR 107 adapter. It is to enable the memcache. And for the last work, we should say that our DTM system can serve as a generic framework to implement more missing core services provided by the data center network. For example, in our data structure, there is an interface. If the developer can implement the schedule method in the DTM schedulable interface, they can just very easily deploy a new scheduling algorithms. And still, we want to do more measurement in real-world public cloud because we want to keep our pace to the industry because we want to get a general idea how the technology evolves. Here's some the publication days during my PhD study, and we still have some work submitted. Hopefully, we can hear good news shortly soon. Thank you.
Thank you, Mr. Wu. I invite the students and